Today we will continue our discussion that we had started yesterday on mixers, right. If you may recollect, we said that as far as this component multiplication is concerned, which is the basic component multiplier, which is the basic component required for modulation and mixing. This can be realized in several ways, and one method was to use a nonlinear device which has some nonlinear characteristics, right. For example, the device in which the current voltage characteristics have a nonlinear behavior, right, like we have in junction diodes or the p-n junction of a transistor. So based on this principle, we can see that if you apply the input voltage, which is a sum of two voltages, one of which could be your which you want to multiply basically, because of the nonlinearity present, the output current would have some product terms, right. And if you can ensure that by suitable filtering you can take out only the desired product term and reject all other components, you have your the purpose is achieved, right. So I will leave this at this point. For practical circuits based on this principle, I would like you to refer to books. The second kind of mixers that we can have is based on the switching principle, which also I believe you have some idea of, and we will just quickly first review what you might already know. So we are looking at some methods of heterodioning today, or mixing. And in particular we look at first the switching modulator, which is very simple. In its simplest form, it consists of an ideal diode followed by a resistance, at the input to which you apply the sum of the two voltages which you want to multiply or mix, right. So one of them, let us say, is the carrier C of t, and the other is the message M of t. Since the diode is considered to be ideal, if you look at the behavior of the output voltage as a function of the diode conducting or not conducting, basically the diode will go through two phases of operation. In the normal mode, in the forward bias mode, it will act as a perfect short between the input and the output, and the output voltage V naught t would be simply equal to the input voltage at that time. So when the diode is perfectly conducting, the output is simply the input, and which is nothing but the sum of the two voltages that you are applying, the carrier and the message. When the diode is reverse biased, the output voltage is 0 if, let us say, this is connected to ground, okay, which essentially means that now basically we have to now see when does the diode conduct and when it does not conduct. To ensure that to get the required multiplication effect that we want, what we will impose, we will impose a constraint that the carrier is all the time or most of the time much larger than the message signal. The carrier amplitude is much larger than the message signal, right. If that assumption is true, then it is clear that whether the diode is forward biased or reverse biased will be essentially dependent on the carrier voltage, right. So whenever the carrier is going through a positive half cycle, right, the diode will be reverse forward biased, and the output voltage will be nothing but equal to the input voltage. When the carrier waveform is going through its negative half cycle, it is less than 0, the diode will be reverse biased and the output voltage will be 0, right. So this is a kind of switching action. Basically what you are doing is you are getting an output voltage which is a product of the input voltage and a 1-0 sequence, right. In this half you are multiplying the input voltage with 1, in this half you are multiplying the input voltage by 0, right. So it's as if your output voltage V naught t is the product of the input voltage waveform Ct plus Mt. Of course this is not the product that you want or apparently want, but actually it leads to the same effect. This is being multiplied by a switching function or a square wave function which we call G sub T naught t, right, which looks like this. Before I say about GT naught t, let us substitute for the carrier, which could be of this kind, plus the message waveform MT. Right, where GT naught t is a periodic waveform which looks like this. So for half the carrier cycle you are multiplying with 1, right. So GT naught t is 1 during that half cycle. For the other half cycle it is 0, and then again it is 1, again it is 0, right. So basically this is the kind of function with which you are multiplying the input voltage, which is the Ct plus Mt waveforms. This is the nature of where the period of this waveform is T naught, which is equal to 1 by Fc, the carrier period, right. Now this does not conclude our discussion, because we do not want this, we want a product between these two, right. Fortunately that is possible when we realize that this periodic square wave can be expanded in terms of a Fourier series, and without going through the details, all of you know what the Fourier series of a square wave is. It contains only odd harmonics. Since this is a square wave which goes through which goes through an excursion between 0 and 1, it will also have a DC component. It's not a zero mean square wave, right. So there is a DC component which is equal to half plus 2 by pi. This is the Fourier series which I am not computing here, but which all of you know and easily compute. These are the coefficients of the Fourier series: minus 1 to the power n minus 1 upon 2n minus 1, and this is a cosine wave of frequency Fc into 2n minus 1, right. This is the 2n minus 1th odd harmonic, right. So it will have harmonics at the fundamental corresponding to n equal to 0, n is equal to 1, right, because we are going from 1 to infinity, third harmonic corresponding to n equal to 2, and so on and so forth, right. So if you now look at this product, V naught t is the product of this into this Fourier series, and as you can see, this product, if you look at if you were to have a band pass filter following this system, if suppose you follow this up with a band pass filter, right. So your V naught t is coming here, you follow this up with a band pass filter, and the output V of t will contain only those terms which are close to this, which are allowed by the band pass filter, right. Let us say the band pass filter is tuned to pass frequencies in the neighborhood of Fc, right. So the output Vt in this case would be, look at the product terms which will be at frequency Fc. There is this constant half which will multiply with AC cosine omega Ct, right, and there is this message Mt which when multiplied with the first term of the Fourier series will produce a component at omega c or around omega c, right. All other components in this term when multiplied with either this or this would lead to frequency components which are multiples of omega c, right, 2 omega c, 3 omega c, whatever, right. they will all be rejected by this band pass filter. So the final output V of t would therefore be nothing but you can write this as AC by 2. I am just writing these two components into 1 plus 4 by pi AC mt into cosine 2 pi FCT, which is your desired modulated signal. Okay. This contains a carrier component plus the DSBSC component that you are looking for. The modulation index is 4 by pi AC in this device, right. So this generates an AM signal. Okay. So this is fine. Now suppose we wanted a pure DSBSC signal without the carrier component. We can still apply the switching idea. The only difference we need to somehow create is that instead of multiplication of alternate half cycles with 1 and 0, we need to multiply the input waveform with plus minus 1 to make this waveform zero mean. The DC component of this waveform should become 0, so that this factor half does not appear, which multiplies with the carrier component in the other term, right. And that is precisely done by a device called the ring modulator. Or the balanced diode modulator. Okay. The typical circuit will look something like this. I am sorry, this should have been like this. So this is a balanced modulator. It is also called a ring modulator. The reason being that these diodes all face in the same direction. As you trace the diodes, they are all pointed in the same direction, right. So if you go along these diodes, they form a ring in some sense. So we call it a ring modulator, right. So we apply we center tap these transformers here, and apply the carrier voltage C of t at these points, right. And your modulating waveform M of t is applied here. The message waveform M of t is applied here, and this is your output voltage, the modulated signal. Let's call it S of t. The principle is more or less the same. When C of t is the positive half cycle, two of these diodes conduct and two of them are reverse biased. Two of them are forward biased. For example, when let us say it is in this cycle, but this terminal is positive with respect to this, that positive half cycle, which diodes will conduct? These two, right, and these two will be reverse biased, as you can see, right, because this end will be at a higher voltage than this end, and therefore it will be reverse biased. Similarly for this, remember that we are assuming that for this discussion that these transformers are short circuits in that sense. So more or less we are assuming that this point is directly connected to this point. So we are assuming that the impedance offered by these diodes at the carrier frequency is very small, right. Similarly, so when these two diodes are conducting, basically what you are going to get is this voltage, which is a sum of once again the carrier voltage and the input voltage, appears across this, and therefore they across the output directly. In fact, more or less you can say that empty directly appears in this case, because CT is actually balanced out, right. There is no net carrier applied from here to here, right, as you can convince yourself. The carrier voltage appearing between these two transformer terminals, if the transformer is perfectly balanced, if the center tap exists precisely in the middle of the winding, right, there will be net zero voltage due to carrier here, and similarly net zero voltage due to the carrier here across these two terminals. So basically this voltage empty, assuming this is unity gain or whatever, will appear across this output and therefore at the output, right. So you will get empty multiplied with 1 at the output in this case. When the carrier is in the other direction, right, now which diodes will conduct? These two diodes will conduct, these two will be switched off. What is happening now? Instead of empty reaching this point here, basically the polarity, the connections are reversed, right. So as if you are changing the sign of empty, right. The positive voltage is going down, and I mean in a manner of speaking, and the negative voltage is, right. So effectively the connection between the input and output is crossed, right, and therefore that is equivalent to multiplication of empty with -1, right. So if you were to plot these waveforms, basically what we are saying is something like this. Maybe this is a better place to plot. Assume this is your modulating waveform, and to show the switching action, basically what we are saying is we are multiplying with this waveform with these positive and negative pulses, or this square waveform which goes between +1 and -1, and the output would be a waveform like that. Of course this switching will be at a much higher rate than I have shown in this picture, because this is a carrier frequency. So this switching is taking place at the carrier frequency, which is a high frequency. So you will get something like that. Right. So during this time you are multiplying with +1, so whatever is appearing across the empty here, it goes across like that. During this interval you are multiplying with -1, so you get something like that. The same message waveform appears with a negative sign, and so on and so forth. Etc. So you get a modulated waveform which looks like this. Of course, once again the carrier here does not appear to be sine wave, it appears to be a square wave, right. So what should I do? If you remember, the basic theory remains the same. Empty is multiplied with the square wave. Square wave contains this fundamental component and its harmonics, odd harmonics. So we want only the component which is a product of this empty with the first harmonic of this, right. So what should we do? Simply pass this through a band pass filter tuned to the carrier frequency Fc. So this output, this ST, when passed through the band pass filter, will produce the perfectly balanced empty cosine 2 pi FCT that you want with a scaling factor of suitable value, right. So that's a balanced modulator for us. For this to be balanced, these transformers need to be perfectly balanced so that the carrier component does not appear at the output, right, so that the net voltage due to the carrier here and here is 0, right. So we require, and also these diodes should be identical, right. If they have a finite, if they are ideal, there is no problem, but if they are non-ideal, they should have more or less the same value of the forward resistance, right. So those are the requirements for making them balanced. You can similarly have other circuits. I think I just wanted to give you a flavor of the kind of things that we can do to generate both AM signals as well as DSP-SC signals, right. Having generated any one of them, one can then generate either the SSP signal or the VSP signal by appropriate sideband filter. Okay. Any questions? If not, then the last topic that I am going to take with amplitude modulation for the time being, I will return to envelope detection once again. Remember, envelope detector is one of the most commonly used detectors for detecting amplitude modulated signals, right. Commonly used because most of the time when you use amplitude modulation, particularly in broadcast applications, you are using it in the amplitude with the carrier, right. It is DSP AM, which has a carrier component, so as to make the envelope proportional to the message waveform M of t, right. And the idea is to have a very simple demodulator using a diode and two RC, one resistance and one capacitance, right, the diode detector. Now when you use this device for detection, we must be aware that there are some limitations of this device, right, and that limitation is what I want to talk about right now. That limitation typically arises in the presence of interference, right. If there is an interfering signal present along with the desired signal, then under certain conditions the interfering signal can take over the output rather than the desired signal, right, and that is something that we must understand. So I would like to spend some time on the effect of diode, how the diode detector works in the presence of interference. Now at the moment I am not taking interference to be noise. Noise analysis is something we will do separately, right. At the moment I am talking of another interfering signal as the interference, right. For example, let us say, just to put this interference idea in a proper perspective, we discussed the super heterodyne receiver yesterday, right, and we said that unless you design your RF filter properly, there is a possibility of the image frequency component coming through at the input to the IF filter, right, and if that happens, because it will happen, that image frequency component will nearly appear at the image IF intermediate frequency itself, and the intermediate frequency filter would not be able to reject it, right, because it is in the neighborhood of the intermediate frequency. So maybe excuse me, maybe you have a desired signal omega c, desired signal of frequency which is a modulated signal around the frequency omega c, right. Along with that we get an image frequency component. If your RF filter is not good enough, that is likely to happen, right. So for example, it could be the image frequency component. Of course this will not happen if your RF filter is designed to reject at least the image frequency, right. But even if this was not the case, there can be situations where an undesired transmitter is located very close to the frequency of interest. Let us say that you are trying to receive a transmitting station at a certain carrier frequency, and there is an interfering transmitter which is also located in the same neighborhood or in the neighborhood of your receiver. It may not be in the neighborhood of your transmitter, but it may be in the neighborhood of your receiver transmitting something else. It may be an undesired transmission. Sometimes you have an RF equipment, it is not supposed to transmit, but there is a leakage, right. You have a receiver and there is a leakage coming from this equipment which works at that radio frequency, which has an internal operation at that radio frequency, and some components may radiate some power, and that power will be getting into your receiver, right, and that will appear as in the form of an interference, right. So that is why we call it a tonal interference. Tonal because there is a sine wave or cosine wave of a frequency close to the carrier frequency which is directly coming in into your receiver along with your carrier frequency, right. So basically what we are saying is that we have a received signal x sub r t which contains the carrier of interest, it contains the modulated signal of interest, and for the purpose of discussion here I am taking the modulated signal to be am cosine omega mt, right. And so this is am cosine omega mt into cosine omega ct. These two are the desired components, out of which eventually I want to get output at the envelope detector output I want am cosine omega mt. I want something proportional to the message signal. I am taking this to be the message signal mt, right. But along with these two things, which is a carrier, the DSPSC part, this, for example, this could be the AM signal that I am receiving, these two together. Along with this I am getting an interfering signal of amplitude A sub I into cosine of omega c plus omega I t. Okay, that is a tone, a pure tone, the cosine wave of frequency omega c plus omega I, where omega I is close to omega c and is therefore not rejected either by the RF filter or by the IF filter. So there is this interference present at the output of the RF filter mixer. This will produce a tone at frequency. Okay, think of this as the output of the IF, right, intermediate stage, intermediate frequency stage. So this is the IF amplifier output, in which case basically what we are saying is that this omega c that I am talking about here is the intermediate frequency, right. So in any case there is a very closely located signal which is not rejected by the IF filter, and that is coming along with your desired signal. And what will be the stage following the IF stage? The diode detector. You will try to detect your message signal by passing this through a diode detector. So we like to now study what happens if the input to the diode detector is not this waveform, which would have been the normal thing, but this corrupted with this interference. Is it clear what we are trying to do? So suppose we have coherent, before we talk about diode detector, let us talk about coherent detector. What would the coherent demodulator produce? Right? What will the coherent demodulator produce? So remember, this is the undesired signal, undesired interfering tone.
So both omega c plus omega I and omega c will be transmitted to same frequency omega IF.
No, think of this omega c as omega IF, right? Normally you at the output of the IF filter you would have only got a carrier at the IF frequency, and both here as well as here. But along with that you are also getting a close by tone which the IF filter cannot reject, right? Think of omega c here as omega IF, right? So this interfering tone is close to that omega IF, and therefore it cannot be rejected. All right. So can you say what will be the output of the coherent demodulator? The coherent demodulator will produce an output corresponding to this, right, which will be equal to, so y dt. I am not going through the details because these are things that you now understand very well, right. You are multiplying this with cosine omega ct and then low pass filtering the result. You will get am cosine omega mt, maybe with some scaling factor which I am ignoring here, right. But you will also get something here right? You will get something proportional to AI cosine omega it, right? So even the coherent demodulator, even in the coherent demodulator, you will get an output corresponding to this image interfering frequency present in the input signal, right? So even the coherent detector would not work perfectly in that sense, right? Not only you get your desired signal, but you get your tone, the interfering tone of frequency omega I. Is that clear? However, the amount of this interference that you will see at the output will be directly proportional to the amount of interference present at the input, which is something that we accept as communication engineers, right? We call this a graceful behavior, right? The output is as bad or as good as the input. Let's put it that way. Input is bad, your output is bad, right? We can't do very much about it. So it is output is directly proportional. Output interfering component is directly proportional to the input interfering component, right? So that's what the coherent demodulator will do. Now how about the envelope detector? To see this, it is useful to take recourse to the phasor diagram. Phasor diagram representation of this signal that we are talking about here. And let's first look at the phasor diagram. Okay, first let's write the whole expression. Let's write this in the form of complex exponentials, because for phasor diagrams it is better to work with complex exponentials, right? So you can think of the received signal x sub rt as the real part of, now the first term was AC cosine omega ct, so it is a real part of a sub c e to the power j omega ct, that is the carrier component, right? Then there is this interfering component which is at frequency omega c plus omega I, right? The cosine omega c plus omega I, that is a sub I, real part of e to the power j omega ct into e to the power j omega sub I t, right? Because this is omega c plus omega I. And then there is a modulated component, right? What are the there are two sidebands present here, one at frequency omega c plus omega m and the other at frequency omega c minus omega m, right? So what are the corresponding phasor components? So this is plus half a sub m e to the power j omega ct into e to the power j omega mt plus half a sub m e to the power j omega ct into e to the power minus j omega sub mt, right? So the real part of all this is that signal, which you can write as the real part of, take e to the power j omega ct term out common, because that is present in every one of these terms. A sub c plus a sub I e to the power j omega I t plus half a m e to the power j omega mt plus half a m e to the power minus j omega mt. And we like to represent this signal xrt in terms of a phasor diagram. Do you know how to do that? I am sure all of you know that, but just to recapitulate, first of all it will be convenient to only look at this square bracketed term. We can ignore this e to the power j omega ct, because you can think that your phasor diagram is being drawn in a reference frame which is rotating at the frequency omega c, right? So every term is rotating at that frequency, so you can now think as if, as far as these components are concerned, you are working in a stationary framework, right? So if everything is rotating, then with respect to this it is stationary, right? So we will only therefore look at these components and draw the phasor diagram corresponding to these. To understand what is happening, let us first draw the phasor diagram without the interfering component. This is the interfering component, right? So let's see what is happening to the received signal. What is the nature of the received signal as represented on the phasor diagram without the interfering component? Okay. So what will you get? You have this carrier phasor with amplitude A sub c, right? Then you don't have this, because we are saying this is at the moment we are not considering this. We have these two sideband phasors, right? With respect to this carrier phasor, which is actually rotating at omega c, but if the whole frame is rotating, it will appear to be fixed, right? This is rotating faster than the carrier phasor, right? So with respect to the carrier phasor, it is having a rotation at the speed of omega m radians per second. Let's say in a counterclockwise direction. So plus omega m, let's say, means rotating in a counterclockwise direction, which I'll denote rotating like this, right? It's going round and round around the carrier. Oh, I'm sorry. All right. Let me take this to be minus omega m. All right? Correct. And then it doesn't matter, you can take any one of them as clockwise in the, it's a matter of notation. This is what you will get, one phasor rotating like this, the other phasor rotating like this, right? And what you will see, the actual signal will be the resultant of all these three phasors, right? Now no matter where this rotation is, it is symmetrical with respect to the carrier phasor at any time t. If at any time t, this phasor will make an angle omega mt with respect to the carrier phasor, this phasor will make an angle minus omega mt, right? So they are symmetrically placed with respect to the carrier phasor, and therefore the resultant wave by your parallelogram method, etc., would appear like this, right? R of t. The resultant will always be along this line. Is that clear? It will, the resultant RT will fluctuate around AC on both sides. For example, at this position, the resultant will lie here, right? So basically what you will see is that the carrier wave is being modulated in amplitude around AC, right? It's going up and down in proportional to the message signal cosine omega mt, right? Is that clear? So that's how the whole thing is working, and the envelope detector will actually follow this. You can think of this R of t, the resultant amplitude, as the envelope. This is the envelope that you will try to trace through the envelope detector. It will be sensitive to this envelope amplitude, envelope value, right? So the envelope detector output here is proportional to R of t, and since R of t here will be proportional to cosine omega mt, this will be proportional to cosine omega mt, as we expect it to be, right? There is no problem about that. I hope all of you are with me on this. Now let's see how things change if we also introduce a sub I e to the power j omega. How will you modify the phasor diagram? Anyone would like to comment? When this component also has to be considered. So we start with the same starting point, that is, you have a carrier component a sub c, carrier phasor, and then what do you have? E to the power j omega I, right? So it's rotating, let's say, like this, sorry, like this, right, at a frequency of omega I radians, right? And now at this point you are superimposing the two side bands, right, which will look like this, because with respect to the carrier they still have the same configuration, right? They are omega mt and minus omega mt, and they will form an angle of plus omega mt and minus omega mt with respect to the carrier, not with respect to this. So they will look like this, right? And their resultant is something here, and the overall resultant is where? Overall resultant would be this waveform, this phasor r of t. So your RT, the overall resultant, is this now. Is that clear? So one of the things that you can see, that now the resultant phasor is not along the carrier phasor. Therefore it is not undergoing only amplitude variations. Amplitude variations will be there as all these phasors rotate. As this rotates and these two rotate, the amplitude also will keep varying, right? But in addition, there is also a phase variation, right? Theta of t. So these two variations are being introduced. So the issue is, what is the nature of this envelope? What can we say about this envelope? It's very difficult in general to visualize what is happening, but it is not that difficult to visualize under some simplifying assumptions, right? So let's study the behavior of this envelope under some simplifying assumptions. By envelope I mean the length of this vector, right? The amplitude. The amplitude is what will be important when we are looking at the output of the envelope detector, right? Because the envelope detector will produce an output proportional to the instantaneous amplitude of the carrier wave, right? Okay, so to do that, let me return to my original expression. X sub RT is equal to A sub C. I did all this just to make you give you a feel for the phasor representation of these signals, which is important, as we will see later. It's very important, particularly when we want to do the noise analysis, both for AM as well as for FM signals. So the phasor representation is something I wanted to introduce at an early stage so that you get used to it. So let's come back to your old expression, AC cosine omega CT plus AM cosine omega MT cosine omega CT plus the interfering term also let me write as, if you remember, it is cos omega C plus omega I, right, which I can write as cosine omega CT cosine omega IT minus sine omega CT sine omega IT. And you know why I did this? What's the motivation for writing like this? Because I like to express this received signal in the quadrature representation. Any narrow band signal we know we can write in quadrature form, right? There is an in phase part which is multiplied with cosine omega CT, and there is a quadrature phase part which is multiplied with sine omega CT. If I have it in the quadrature form, I can easily identify the nature of the envelope by taking the square root of modulus of the thing, right? So it will be, what is the in phase part? It will be AC plus AM cosine omega CT, cosine omega MT plus AI cosine omega IT. This whole thing multiplying cosine omega CT. Right? I have collected all the terms containing cosine omega CT together minus the quadrature part, which is AI sine omega IT into sine omega CT. So we like to understand the nature of this envelope under at least some simplifying assumptions. In general, it is little difficult to appreciate. Okay. What can we say? Let me make the simplifying assumption that let us take case 1, that A sub c is much greater than A sub I. This is a simplifying assumption, right? We are saying that A sub c is much greater than A sub I. Now we have had some discussion of the behavior of the envelope detector under these kinds of conditions. Do you remember we discussed this in some other context? In the context of demodulation of SSB and VSB signals by the carrier reinsertion method, right? So it's the same kind of situation here. If this is much greater than this, the envelope will be dominated by which term? The first term, right? Because you take the square of this and the square of this, add them up and take the square root, right? But the square of this will be much smaller than the square of this, you can ignore it, and therefore essentially it becomes a square root of the square of this term, right? Therefore in this case the second term is negligible, and your demodulated output, if you forget the DC component, right, A sub c will be the DC component in the demodulated output, which is of no consequence, we can ignore that, will be A sub m cosine omega mt plus A sub I cosine omega it, which is perfectly fine. This is precisely what we got when we use the coherent demodulator. If you remember, some time ago we discussed that, right? This is precisely the output that was produced by the coherent demodulator. So no problem. So under the situation that the but only thing is, here we have obtained this result under an assumption. What is there? There was no assumption. That is the difference. The assumption here is that the interfering component is much smaller than the signal component, the carrier part, right? So the carrier there was we had to make no such assumption for the coherent demodulator. It will always produce this output, right? No matter what is the value of AM and AI. If AI is large, of course the output will be large. This will be large. If AI is small, the output will be small. That's true even here. But for this to work like this, what we are saying is the carrier component must be much greater than the interfering component. That's what we are saying. To appreciate the significance of this assumption, let's take the opposite situation. Okay, the opposite situation is that AC is much less than A sub I. Okay, now relook at this expression. What will you get? It's difficult to say directly from this. So what we do is we slightly manipulate this expression once again. This expression for XRT. Difficult to say because A sub I is appearing here as well as here, isn't it? That is why it is difficult to see what is happening. If it was appearing in only one of these two terms, it would have been very easy to say. But since A sub I is appearing in both these terms and AI is very large, it is difficult to say directly from this. So what we do is slightly remanipulate this expression as follows. I am writing the first term cosine omega ct as A sub c cosine. This is a trivial kind of thing that I am writing, but it has a significance which we will soon see. I am writing like this: omega c plus omega I minus omega I, right, t. Then we have the interfering term which was ai cosine omega c plus omega I t, right. I think very soon you will all see what I am trying to do. And then am cosine omega, this is the moderated part, am cosine omega mt into cosine omega c plus omega I minus omega I t. Same thing. Everywhere when I have only cosine omega c, I am replacing it with omega c plus omega I minus omega I. And I think now you probably already know what I am trying to achieve. I am going to write an expression in which the carrier is not omega c, but omega c plus omega I. That's basically what I am trying to do in this, and the reason will become very clear. So if you expand this now as cosine A plus cosine A minus bt, etc., and then simplify, maybe I can skip that trigonometry and give you the result directly, because that's straightforward. You get finally this expression. You get x sub rt is equal to a sub I plus a sub I, a sub c cosine omega it plus am cosine omega mt cosine omega it into cosine omega c plus omega it plus a sub c sine omega it plus a sub m cosine omega mt sine omega it into sine omega c plus omega I t. So once again I have a quadrature representation. So please assume this is correct. This is just coming out of. So important thing is, instead of writing it in terms of quadrature representation using omega c, I have used omega c plus omega I. Why did I do that? Now that will be obvious from here. As you can see, this second term now does not contain a sub I, because earlier a sub I was present in both the terms. Now it is present only in the first term, right? And therefore we can say that the first term will dominate the envelope detector output, right? Because this is much larger than AC. We are saying that a sub I is a very large interference, right? So this term will dominate the output, and therefore you can say that your envelope detector will produce an output y sub dt, which is approximately equal to, if I forget the DC part, right, a sub I is some DC component, AC cosine omega it plus am cosine omega mt cosine omega it. Now this is very interesting if you look at it carefully. What are the conclusions you can draw from this? First conclusion from this discussion is that as the envelope detector now thinks that the carrier is not omega c, but the carrier is omega c plus omega I. So in a way, the stronger of the two components capture the envelope detector output, right? Captures the receiver, right? If the interfering component is stronger, it captures the receiver, right? It will produce it will dictate what the output of the envelope detector would be, right? Rather than allowing the signal component to, the carrier component to dictate, right? And once it dictates that, the output has no resemblance to the message signal. That's the second conclusion. The output now is, you see, your message signal was containing a component at omega m, right? So the input was, there was a message component at frequency fm, and there is an interfering component at frequency f sub I, right? If at the output I got these two components, no problem. That's what the coherent detector does. It produces both these components at the output. Fine, because the input contains interference, the output should contain interference. That's fine. However, what I am getting here is, I don't get FM at all, right? What you are going to get is this component f sub I, there is this component f sub I minus FM and f sub I plus FM. We don't even have a component at the desired signal frequency. Message frequency was f sub m. There is no component in the output at the frequency f sub m. The interfering tone and plus minus FM, these are the frequency components present in the output. therefore there bear no resemblance to the actual input signal, right. This output signal will be quite distorted. So in a way, the presence of a large interfering signal degrades the output to the extent that it, as if modulating signal is actually modulating, not the is not coming out, but it's modulating the interfering tone, omega sub I. Right? So I think I hope you understand then that the analog detector works very nicely as long as the interference is small, but if in some situations the interference becomes large, this doesn't work well. That will be our conclusion for today. Thank you very much.